In this video, we're going to solve differential equations using the inverse Laplace transform. We're going to review partial fraction decomposition. We're going to find the inverse Laplace transforms, and we're going to solve ODEs using Laplace transforms. So we know from our previous video, 6.1, that the Laplace of f prime of t would be equal to s, the Laplace of f of t, minus f of 0. And the Laplace of the second derivative would be s squared Laplace of f minus s multiplied by f naught minus f prime evaluated at 0. And we can use this to solve our ordinary differential equations. So for example, we can solve for x prime of t plus 2x of t is equal to e to the t when we have x of 0 is equal to 5. But before we do this, we need to have some new definitions, and we need to review a little bit about partial fraction decomposition, which you should have seen in your Calc 2 class. So here's our definition. We say f of t has a Laplace transform, capital F of s, is called the inverse Laplace transform of f of s, and is denoted by this funky looking L, the script L raised to the negative 1, so the inverse, of cap f of s. As long as we are working with piecewise continuous functions of exponential order, the inverse function will be unique, except possibly at the points of discontinuity. For any continuous function, lowercase f, of the exponential order, the Laplace inverse of Laplace of f of t is equivalent to f of t. So the inverse Laplace transform is a linear operator, which means that finding the function x of t has a Laplace transform capital X of s is inverting the Laplace transform. And basically, it means that we take our table that we got from section 6.1, and instead of going from left to right, we go right to left. But what happens if I can't find this cap X of s? Well, we know from pre-calculus 1 or from calculus 1 or calculus 2, we can decompose using partial fraction decomposition. So as an example, if I have this p, which is a polynomial, p of x over q of x, which is a polynomial, I could rewrite it as a over x, a sub 1 x plus b sub 1, etc. And then, of course, if they're non-repeating linear factors. So how do we do this? Well, if I have non-repeating linear factors, then I have this a1, a2, a3 underneath or on top of, the numerator thereof, of each one of those individual linear factors. Now, if that linear factor is repeating, then of course I would have all the combinations. So if this was, say, to the third power, then I had a sub 1 of this factor raised to the 1, 2, and then all the way up to the third power. If my factor of q is irreducible quadratic over the reals, then I would have in the numerator, I'd have ax plus b. I'd have a linear. So I always have 1 degree less in the numerator than I have in the denominator. And then after we write the appropriate decomposition and solving, it's like what you would expect. So let's take a look at this example in which I'm asked to figure out what the appropriate a, b, c, d, e, and f are when it's equal to this polynomial. And then we'll do a partial fraction decomp down here. So what I'm going to do is I'm going to think anything in which my a to the fifth, so I'm going to start with, x to the fifth. The coefficient on the left side is 1, and the right side is a, so that a is 1. I'm going to go x to the fourth. The coefficient on the left side is 3, the coefficient on the right side is b. X to the third, coefficient on the left is 2, c on the right, x squared, coefficient on the left is negative 1, d on the right. The x then would give me 1 on the left, e on the right, and then my constant. I have 5 on the left and f on the right. And so now I've found what each one of those coefficients are. So if I take a look at my next example, and I want to do the partial fraction decomposition, then the first thing I'm going to do is factor the denominator. So I have negative x squared plus 2x plus 4 all over, factoring out an x. I'm going to have x squared minus 4x plus 4. This factors again, so I have negative x squared plus 2x plus 4. And then the denominator, I'm going to get x x minus 2, the quantity squared. Now, when I start to do the partial fraction decomposition, I'm going to use this. I'm going to use the negative x squared plus 2x plus 4. I have x minus 2, the quantity squared. So I like using a, b, c, but you can use whatever. So I have a over x plus b over x minus 2, and then plus c over x minus 2, the quantity squared. Now I'm going to multiply everything by my lowest common denominator so that I can clear out my fractions, which happens to be x minus 2, the quantity squared. So each one of the terms is going to be multiplied by the lowest common denominator so that I can clear my fractions. That includes on the other side as well, so x minus 2, the quantity squared. Now clearly in the denominator you can see that those will cancel, so I'm left with negative x squared plus 2x plus 4 is equal to a. The only thing that cancels in the first grouping is just the x, so I have x minus 2, the quantity squared, plus b. X remains and x minus 2 cancels and 1 remains. And then lastly, I get just cx. So what I'm going to do is I'm going to go ahead and multiply out. And so I'm going to have ax squared minus, and that should be a minus, not plus, minus 4x. Oh, don't forget that a. So a is going to be distributed all the way through. Minus 4ax, and then plus 4a. Distributing the bx through, I'm going to get bx squared minus 2bx, and then plus cx. I'm going to start with my x squared term. On the left-hand side, I get negative 1. On the right-hand side, I have an a and I have a b. So a plus b. Now remember, it's coefficient to coefficient. On my x term, I'm going to have 2 on the left-hand side. I'm going to have a negative 4x, negative 4a, excuse me, and a negative 2b. And I also have a c. Now I'm going to work on my constant. And with my constant, I get 4 on the left. On the right-hand side, I get 4a. Well, that's lovely, because that tells me that a happens to be 1. If a is 1, then b, here, coming in back, substituting that in, I have negative 1 is equal to 1 plus b, so b must be equal to negative 2. That means c, which would be equal to 2 plus 4a plus 2b, c must be equal to 2 multiplied, or excuse me, plus 4 multiplied by 1 plus 2 multiplied by negative 2. So c must be equal to 2. So what I know then, after going through this, I know I have negative x squared plus 2x plus 4 over x minus 2, the quantity squared, can be rewrote as my a value, which was 1 over x, plus my b value, which is negative 2 over x minus 2, plus my c value, which is 2 over x minus 2, the quantity squared. And that is the partial fraction decomposition. So I'm not going to go through these. I mean, they're pretty straightforward. You just have to know, like this last one. I'm just going to jump to this last one. That you would write this as the ax plus b over the first irreducible, which is x squared plus 2x plus 9, and then plus cx plus d over x squared plus x plus 5. And then you're going to do pretty much what I just did. Now, if you don't like using a, b, and c, you're afraid about going through the entire alphabet, use a sub 1x plus a sub 2 over x squared plus 2x plus 9 plus a sub x3 plus a sub 4 x squared plus x plus 5. And you can go from there. Now, this is the meat of it. Find the inverse Laplace transform. So what I'm going to do is I'm going to mess around with that, not being able to bring it in correctly for a while. Zoom it in, but there it is. I'm going to rewrite this as 6 multiplied by 1 over s. Now remember, my s's are script because otherwise they look like 5s to me. I don't have to do with anything with 1 over the s minus 8. I'm going to leave that like it is. But I'm going to write this as 4 I'll multiply by 1 over s minus 3. And the reason I'm going to do that is so that I can see that 4 is just a multiplier. Now I'm going to get my Laplace transform chart out. I'm going to look for 1 over s. I'm going to look for 1 over s minus a and 1 over s minus a for the other one. And so what I'm going to get, when I see 1 over s, I get 1 and then minus. This becomes e raised to the 8t using my Laplace transform. And then this last one will be 4e raised to the 3t. Now there isn't much more I can do with that, so I'm going to leave it just like that. So there's my answer, give or take. And this is f, lowercase f of t. It's lowercase f of t. If I take a look at my next example, partial fraction decomposition isn't going to help me because I'm going to get something that says a sub 1 is 6, a sub 2 is 5. Doesn't help me. However, if I have a plus b over c, I can write this as a over c plus b over c. So I'm going to rewrite this as 6s over s squared plus 7 minus 5 over s squared plus 7. Now in my Laplace transform sheet from last video or last section 6.1, I have one that is s over s squared plus a squared. And when I see that, that then becomes the cosine of at. So I know that this first one is going to be 6, this first term is going to be 6 multiplied by the cosine of the square root of 7 times t. Okay, because it is a squared. Now, I don't have a 5 here on any of them. I have an a, and my a, as you can see, is actually the square root of 7. A equals the square root of 7. All right. So what I'm going to do is I need the square root of 7 here, not 5. So I'm going to pull that 5 out. So it'll be minus 5. Now the thing is I need the square root of 7 in the numerator. So if I write this as 5 multiplied by the square root of 7 over the square root of 7, then not only am I going to pull out a 5, I'm also going to pull out the denominator, which is the square root of 7. Then this is going to be negative 5, the square root of 7, divided by the square root of 7, square root of 7. So let me write this as a square root of 7, square root of 7. Then I'm going to have the square root of 7 over s squared plus 7, which of course my a is 7. So the adjustment I made was multiplying by 1, which is the square root of 7 over the square root of 7, but also by pulling out the square root of 7 in the denominator part of that 1. That allows me to have the square root of 7 in the numerator, which is a. If a squared is 7, then a has to be the square root of 7. And then it'll be the sine of 7, square root of 7 multiplied by t. And this is my f of t. With h here, what I'm going to do is I actually am going to do partial fraction decomp because I know this is going to be s minus 5 and s plus 2. So I have s plus 7 over s minus 5 multiplied by s plus 2. This is going to be a over s minus 5 plus b over s minus 2, or plus 2. Multiplying everything by the common denominator, I'm going to get s plus 7 is equal to a s plus 2 plus b s minus 5. See, that's how come my 5s look like 5s, but my s's look like 5s. That's why I do the script. Notice how I did that so fast, it kind of looks like an s. Anyways, I digress. So I get s plus 7 is equal to as plus 2a plus bs minus 5b. Starting with the s term, I get 1 is equal to 2a plus, just a plus b. And then with my constant, I get 7 is equal to 2a minus 5b. I have two equations, two unknowns, and so I'm going to multiply the top one by 5 and add these together. And when I add these together, I'm going to get 5 plus 7, which is 12. is equal to 7a, because my b's cancel. A is equal to 12 over 7. So once I have my a as being 12 over 7, I can find my b. I get my b to be, let me see, if I got 12 over 7, my b must be negative 5 over 7, because I need to add up to 1. So this becomes a, which is 12 over 7 over s minus 5, and then plus negative 5 over 7 s plus 2. Now I go look up, again, I know that I can rewrite this as 12 over 7 multiplied by 1 over s minus 5. Similarly, the same with the negative 5/7. And I go look this up in my right side of my Laplace transform sheet. And so I'm looking up the 1 over s minus a. So this is going to be 12 over 7 e raised to the 5t, because it's a minus a. And then it's going to be minus 5/7 e raised to, well, if it's a plus 2, it must be a negative 2 here. And here is my f of t. Okay, so now that we've kind of got an idea of how to find the inverse Laplace transforms, here's how we're going to use Laplace transforms to solve differential equations. We're going to take the Laplace transform of both sides of the equation and set them equal. We're going to enter the initial conditions of any. We're going to solve the equations algebraically for the transformation of cap x of s of the unknown function x of t. Then we're going to invert cap x of s to find the small lowercase x of t. So let's go ahead and do that. Okay, now remember what we set up in the very beginning of this video is that when you take the Laplace transform of f prime, or in this case t x prime of t, this gets replaced with s multiplied by the Laplace transform of f of t minus f of 0. And the other thing you have to remember is the Laplace of the second derivative is going to be equal to s squared, the Laplace of f of t minus s of f of 0, the initial f of 0, and then minus f prime of 0. So we know that just this portion is going to be replaced with the s of cap x of s, because that's what this is. This is cap x of s. Okay? And then minus cap x of 0. That's what this is cap x of 0. And then plus 2. When I do the Laplace transform of this, it just becomes cap x of s. On the other side, we have e raised to the 3t. This becomes 1 over s minus 3. Now we can see that we have the cap x of s here and here, so we can factor that out. So we have cap x of s. I am left with an s plus 2. My initial condition gets replaced with 5. So minus 5 is equal to 1 over s minus 3. So I have cap x of s, s plus 2, is equal to 5 plus 1 over s minus 3. So cap x of s, s plus 2, is equal to, and then on the other side, I'm going to multiply both the numerator and denominator 5 by s plus minus 3. So I'm going to have 5s. And then I'm going to have 5 is 15 minus 1, so 14. And then I'm going to have s minus 3. Now, to solve for cap x, all I have to do is divide both sides by s plus 2. So cap x of s is equal to 15s minus 14 over s plus 2 multiplied by s minus 3. Now you're like, how did we get to the answer from here? Because shouldn't my answer be t? And the answer is yes. So now what do? Is I take this and I do the partial fraction decomp. So I do 5s minus 14 over s plus 2, s minus 3. When I do the partial fraction decomp, what I'm going to get is 1 over 5 s minus 3 plus 24 over 5 x plus 2. S plus 2. S plus 2. Now, what I'm going to do is I'm going to go out to my Laplace transform. I'm going to look on the right-hand side. And x of t is going to be equal to 1/5. The s minus 3 is e raised to the 3t plus 24 over 5 e raised to the negative 2t. And there is my answer. So very, very sweet. Let's take a look at my next example. I have y double prime minus 10y prime plus 9y. Now, remember when I do the Laplace transform of y double prime, I'm going to come back up here. Y double prime is going to give me s squared, the Laplace of f of t, or actually y of t. Use y of t minus sy of 0 minus f prime, y prime, I want to keep going to use y prime of 0. And that's all for the y double prime. Now, this next piece, I'm going to use, this next term, I'm going to use this one. And so I have minus 10. Now in here, I'm going to have an s, the Laplace of y of t minus y of 0. And then I'm going to have plus 9 cap y of s. Now, this is equal to 5t. So when I look up the t, I'm going to get 5 over 1 over s squared. Now, we know when we see this gets replaced with a cap y of s. So I get s squared cap y of s minus s y of 0 minus y prime of 0 minus 10. Remember, this gets replaced with cap y, so s cap y of s minus y of 0, plus 9 cap y of s is equal to 5s squared. All right. Now, I'm going to go back and do the replacements for y naught. So y naught, y of 0 that is, y of 0 is equal to negative 1. So this becomes s squared y of s minus s multiplied by negative 1 minus, that gets replaced with 2, so minus 2, minus 10 s cap y of s plus, and then y of 0 gets replaced with negative 1 multiplied by 10. Negative 10 multiplied by the negative y of 0 is positive, so that's why it's a positive. Y of 0 is negative 1, so it's a 10. And then plus 9 cap y of s is equal to 5s squared. Now I'm going to collect up all my capital Y's and factor them out. This one has a capital Y, this one has a capital Y, and this one has a capital Y. So I have capital Y of s squared minus 10s plus 9. What's left over then is, well, this is positive s. So I have positive s. So plus s. I have negative 2. I have negative 10, so I have negative 12 is equal to 5 over s squared. Now I'm going to move my 12 minus, or s minus 12 to the other side. So I'm going to get capital Y of s multiplied by s squared minus 10s plus 9 is going to be equal to 5 over s squared plus, well, I'm going to move the s to the other side, so it'll be negative s, so it'll be 12 minus s. Now I'm going to divide both sides by this, which is the same thing as s minus 9, s plus, or s minus 1. So capital Y of s is going to be 5 s squared s minus 9 s minus 1 plus 12 minus s over s minus 9 s minus 1. I'm going to combine these two, so cap y of s. When I combine these two, I get 5 minus 12s squared minus s cubed all over s squared 9 minus s minus 9 s minus 1. I'm going to do the partial fraction decomposition on this, and what I end up with, the y cap y of s is equal to, I get 50 over 81s plus 5 over 9s squared plus 31 over 81 s minus 9 minus 2 over s minus 1. Again, I'm going to go out to my Laplace transform, and this time I'm going to look on the right-hand column. I'm going to look for 1 over s. I'm going to look for 1 over s squared. I'm going to look for 1 over s minus 9, or minus a. And again, 1 over s minus a there. So then my lowercase y of t becomes 50 over 81 plus 5 over 9 t plus 31 over 81 e raised to the 9t minus 2 e raised to the t, and there it is. Now, I personally think it's kind of easier, but you may not find this kind of easier, but there it is. Let's take a look at one more example here, and then we'll call it a day for this video. So once again, I'm going to do 2. Remember what y prime gets replaced with. It gets replaced with s squared cap y of s minus sy of 0 minus y prime of 0. So that is all the replacements for y prime. Y double prime. Y prime gets replaced with, so we have 3 s cap y of s minus y of 0. And then the 2y, so this becomes minus 2 cap y of s. I'm going to need this space, so I'm going to go ahead and erase this. Erase all of that so I can have this space. On the other side of the equal sign, we have te raised to the negative t. Looking on my Laplace, this becomes 1 over s plus 2, the quantity squared. Once again, I'm going to combine up like terms. So I would distribute the 2, I distribute the 3, and what I'm going to end up with is 2s squared plus 3s minus 2 multiplied by cap y of s plus 4 is equal to 1 over s plus 2, the quantity squared. Bring in the 4 to the other side, and then dividing, I'm going to get cap y of s is going to be 1 over s plus 2, the quantity squared. 2s squared, oh, I should probably consider factoring this. So let's go ahead and factor this before I move it. This factors into 2s minus 1 and s plus 2. So then I'll have a 2s minus 1 and an additional s plus 2. So I'll combine those in a minute. Minus 4 over 2s minus 1, s plus 2. And as before, we're going to bring this into a single fraction. So cap y of s is equal to negative 4s squared minus 16s minus 15 all over 2s minus 1, s plus 2, the quantity cubed. I'm going to do my partial fractions, and this is going to be a whole lot of not fun. When I do my partial fractions, I'm going to end up with cap y of s is equal to, what I found was that all of them have a denominator of 125 for my A, B, C, and D, give or take. So after I found my A, B, C, and D, I am going to factor out 1 over 125. What I'm left with is negative 192 over 2 s minus 1 half. Now, the reason I'm doing that, because it's negative 192 over 125, but this s minus, it needs to be s minus 2, and this is 2s minus 1, so I'd factor out a 2, giving me a 2 here. And then I'm going to get 96, and it would have been over 125, so I'm just going to write it as s plus 2. And then minus, now this one would have been actually negative 2 over 25, but since I factored out 125, this will be 10, negative 10 over s plus 2, the quantity squared. And then my last one is going to be 25 over s plus 2, the quantity cubed. So then my y of t will be equal to 1 over 25. 1 over 125. These two cancel down, of course, leaving me negative 96e raised to the t divided by 2, in other words, t times 1/2, plus 96e raised to the negative 2t, minus 10t e raised to the negative 2t, minus 25 over 2 t raised to the third, excuse me, t squared, e raised to the negative 2t. And there's my final answer. So that's it. It's kind of nice if you're good with partial fraction decomp and all the many steps, but it's also, I think, kind of nice compared to some of the stuff we've done. That's it for this video.